Containers are a pretty complicated piece of software engineering technology, and nothing really shows that best than the people who try to exploit them. And in today's video, I'm going to focus on exploits found in containers and apps that utilize containers for their development process. And if you're new here, this is Hacktivity Explained, the series where I look at bugs found by normally other bug bounty hunters so that we can analyze them and learn from them. And the goal is not to just admire the vulnerability and understand it, but to actually dig deep and figure out its root cause, like why the developers made this mistake, what assumptions did they make that caused it. And those are things that are very important to understanding vulnerabilities and actually applying them to our own bug bounty journey as well. And our first report is in an application called Semel. I think it's Semel, maybe Semi. I'm not sure. Either way, this is an application, or was an application because it was acquired by GitHub, where basically when you had your source code, you would have it there. And when you sent it to Semel or Semi, they would build it into a Docker container and then run vulnerability analysis on it inside like this containerized environment. So it was kind of like a unit test, if you know what that is, if you're a programmer, just on like the whole application from a security perspective. And the way you told Semel how to build these containers is with this lgtm.yaml file, which is probably like a very primitive Docker file or something that looks like it. It looks a bit like it as well. And this basically told Semel how the application should be run in a way that's, in like the actual environment for the application, because different applications are going to require different setups, different databases, different backends or whatever. So having a file like this is effectively essential to correct vulnerability analysis. The other thing is that they had like a web application. So they had a web application where you could actually view the Docker container and you could view specifically the source code that you actually uploaded. So let's say some developer uploads the source code to this Semel application and there's some vulnerability testing going on. Then some manager could log on and be like, oh, this got uploaded, and then he can read all of the files that were uploaded, just as like a verification check or whatever, including this lgtm.yaml file, basically. That was included. And basically you could have this in two forms. So you could have either this lgtm.yaml file, or you could have .lgtm.yaml file. So in Linux, if you don't know, the dot before a file means that the file itself is hidden. So if you open it in like a command, in like a folder, or you do ls on the directory, it won't show it to you unless you explicitly specify that you want to see hidden files, which in Linux is the ls-a command. That'll show you all the files. That's important to realize. So these configuration files often have bugs. These configuration files are often buggy, just because developers kind of, it's hard to implement this. You can't really blame them that much for it, and there's a lot of different things that can go wrong here. And in this case, the thing that went wrong is with symlinks. The developers kind of forgot about symlinks. What is a symlink? In Linux, you can have two types of files, just a normal file with its contents, or you can have a symlink, which points to the contents of another file. And basically, most commands, if you try and read a symlink, it will actually read the contents of the file it is pointing to, just by nature of the operating system redirecting you to it. And in general, you have to specify specific flags on commands for it to explicitly either not follow symlinks or like not read the symlink or output the actual content of the symlink, which is usually just the actual absolute path of where the file is. And developers forget about this mainly because you have to do, it requires configuration to not do, which are the best vulnerabilities are where the developers have to take steps to prevent them. We don't want vulnerabilities where the developers have to take steps to cause them. The ideal vulnerabilities where a developer has to take steps to prevent the vulnerability, because chances are they're going to forget because they're like overworked and burnt out and stuff like that. So we want to abuse that as much as possible. And basically this hacker figured out that when you created one of these configuration files, specifically when you had two of them at the same time, So there was two options, the lgtm.yaml and the .lgtm.yaml. And if you included both of them, the program would get a bit confused and use the first one, but still kind of process the second one in some way. And when I mentioned the file viewer, what the program actually did was when you uploaded the source code to it, it automatically copied that source code into another directory or folder or whatever, so that it could display the files to you. But what happens if you copy a symlink? If you copy a symlink by default in Linux through the command to copy a whole directory, what will happen is the symlink will be resolved to the file that it's pointing to. And this is a bit of a weird design on Linux. I think that this is probably a little bit dodgy. But if you uploaded a symlink as this .lgtm.yaml file, what would happen is when the program went to copy the directory, that symlink would get resolved. And if you had that symlink pointing to a file on the host machine that you were not supposed to read, like in this case the etc/password file, when the program went to copy it over, it would literally include the contents of the file in the symlink, which means that this is a local file read vulnerability. And that was obviously marked as critical because you could read any files, which is pretty cool. This is really great if you can just do this. That just seems like, honestly, if you can ever get like this where you can just say, hey, I have your etc/password file, I think that's like mad. Or if you can get something like this, that's just like, give me that critical vulnerability, But yeah, that's pretty cool. And you set up the project. To make a symlink on Linux, I think you just have to do like ln and then the file and then the file you want it to link to. So it's pretty handy. Now, one thing that I want to say is that, I was doing some research for this video, was that this is not the first time that this has happened to the same company from the same hacker. I managed to find this second report that was literally submitted a week before the other one. So this is the one that we just covered. This one was submitted a week before the other one. And it's literally the exact same vulnerability. Basically the exact same vulnerability. The same attack. It's basically, instead of this using this configuration file .lgtm.yaml, instead it uses a log file that was automatically generated by the server. Like here, this option.out.snapshot.log.build.log, which was accessible to the application, so the Docker inside a Docker container. And what it basically did is, during the building of the inside the configuration file where you tell the Docker container how to build your actual application, you just say to switch that log file to a symlink instead. And that symlink is going to point to the etc/password file. And this log file also gets copied over by the application. And when it does that, it also resolves the symlink, because by default it usually will resolve the symlink. And I think that's very funny, because it's literally like the same attack and it happened to the same company within a week. So this is really showcasing you that when there's like one kind of mistake a developer made, it's also likely going to be in the other areas. And really, the root cause of the vulnerability is developers assumed that the files that were on their machine were going to be safe. That copying them over, there was not going to be any risk of user input being in there, because they're already on their machine and they've been presumably sanitized or whatever. But that assumption was wrong, because you can include symlinks and files on the functions on Linux, so the commands on Linux automatically resolve them. So that's how this mistake happened. And I think it also does teach you that whenever there's one developer coding something, it's probably the same guy that coded this, by the way. Whenever there's a developer coding something, if he made one assumption in one place, he probably made that assumption in other places too. So it's worth checking it, and you can literally get 2 back-to-back criticals like this fella did. That's a very cool vulnerability. Rewarded $2,000. This guy testanull, which is very interesting, and it's apparently privilege escalation, which is probably not correct, but yeah, 2 very nice vulnerabilities. It really shows you how you can use the functionality of containers against the application itself. Now, this next report isn't really a bug bounty report like in the traditional sense. This wasn't actually reported to any programs, but it is a really nice crash course on how to actually do privilege escalation on containers, how to basically escape containers and infect the host. And in this case, the target was Google Cloud Shell. Google Cloud Shell, don't know, it's like this application where you basically just have an online web shell and you can use it to code your website. You have like a Visual Studio Code thing in there. You can access Google APIs, which is, I think, the main reason people use this is you can code like small Google API apps, like Drive apps or whatever. And it's a bit easier to do than doing it normally because your API keys are already included and you can just make a request directly. So that's kind of nice. And basically in this application, when you got onto it, it looks something like this. And you start off with the root privileges on this container. So you already did the root, and you can do sudo su on the container. Now in these kind of applications, you're kind of expecting two things, right? Well, one, you're going to be in a Docker container, right? That's pretty obvious that they're not just going to let you get a shell on the host, right? So this is most likely a container. The second thing you can probably expect is that you're in a Kubernetes node. So Kubernetes is different from Docker. Kubernetes is a way of managing multiple Docker containers using something called nodes. So Kubernetes is a bit complicated, but essentially the server that you're on is the node, and then the actual container plus all of its like services, like maybe databases or whatever, is called a pod in Kubernetes. So when you're on a node, it's going to spawn multiple pods inside of it usually. And when you're inside of a container like this, you're going to presumably be in a Kubernetes pod. And the way you can figure that out is usually you can check if there's a service account or whatever inside of it, but you can also see if it's pointed on a path like this. So if you run like proc/1/c group or proc/self/c group, I recommend running, it would show you basically that you're inside of a Kubernetes instance. This KAS is just a classic Kubernetes path. And this is a lot harder to escape than Docker is to escape, mostly because Kubernetes containers tend to be on different servers. So if you want ultra isolation, you have one host running one pod on it, and then they're separated from each other. And the node doesn't have to be like a standalone like brick, like server or whatever. It can also be a virtual machine. So the distinction between a container and a virtual machine is that in a container, the container shares the same kernel as the host and is literally just like a directory mounted on the actual host itself, while a virtual machine has a separate kernel and is like a completely separate file system and all that. So it's much harder to escape a virtual machine than a container. So Kubernetes is pretty secure in that case. And so even if you manage to escape the container, you would have to look to escape a virtual machine after that, which, good luck with that. That's very difficult. But anyway, you're inside the container first. So let's look at how we can escape the containers. The first thing that you can do here, this attacker did, or the hunter did here, is that they checked what kind of privileges they have here. So in this case, they used proc/self/status and checked the cap effect. When you're creating a Docker container, as I kind of showed you before in the last video on Docker containers, you can assign different privileges, and some of them are less powerful than others. For example, you have like things like cap kills. You can like kill different processes and stuff like that. And some of them are very powerful, like cap system admin. You can see here is a very, very high permission capability that basically allows you to do a lot of things that you shouldn't be able to do. And this is going to allow us to escape the container. When you see this, you can pretty much always escape the container because you have like permissions to do a lot of things. And in this case, there's a lot of ways to escape now. You have a lot of possibilities, and you can basically start from the easiest one and work your way down. And just the easiest way to escape first is to actually try and load your own kernel. Now, this cap system module capability allows a Docker container to load a kernel onto the host. And this guy did like a write up on it here. And basically, because Docker containers and the host share the same kernel, if you modify the kernel on the Docker container, it's also going to change the kernel on the host. And the kernel basically will allow you to get RC, right? So if you can upload a malicious kernel, you're going to be able to get RC on the host, because that's what runs the system and stuff. So once you're able to do that, you can run your own kernel and you should be able to get RC, except there might be a little bit of an issue, because in this case there was a kernel signature verification. Now, I didn't know what this was when I was reading this, but I looked into it a little bit, and it seems like it's something, as far as I know, developed by Google, and it's inside their Kubernetes engine, so it makes sense that they're using this technology. And what this does is that when you have a Kubernetes container, the actual kernels that you can load onto it are locked to a certain amount of modules that are cryptographically signed by the Kubernetes cluster at the start. So you can't load any modules that aren't verified by the Kubernetes cluster. And I think the way this works is that the actual engine itself has a private key, and it will sign the actual entire contents of the what's called the kernel into a hash. And if that hash is stored somewhere on the server, and when you try and load a kernel, it will match that hash against the signature of your kernel, and if it doesn't match, then it's not going to let it through. I think that's how it works, right? I'm not entirely sure, but either way, this is something that Google developed, so it makes sense that their systems are using it, right? And in that case, we won't be able to load up any modules. So this attack vector is basically dead instantly. Okay, what's the another attack vector? The other attack vector is Linux C groups, specifically this version 1. What is a C group? A C group in Linux is a way of taking multiple threads, or processes, making multiple processes in Linux, and basically limiting the amount of resources they can consume. And this is really what makes containers possible. So if you have a container and you want to limit how much CPU it can consume or how much GPU it can consume, then you set up a C group for it, and then you put limits on how much you can consume. And here's a little diagram of how this is the version 1 of how it looks inside the actual file system. So you have these resource types here: memory, disk I/O, and your CPU. And then in this case, you define your groups, and then you have processes for each of those groups. And basically, this allows you to limit the resources here. So you have groups and then actual resources themselves. This was changed in version 2, where I don't think they have this anymore, just they have the actual group sitting on top, and then for each process, you actually define a CPU cap. And this is what Docker uses to limit the consumption of containers, and it's also what Kubernetes uses. Now, the attacker here is using a payload here, and the idea is that we're trying to target this notify on release binary. So in C groups version 1, you had this binary where whenever one of the C groups was released, so it was no longer used anymore, it would trigger some kind of binary on the host to run, some kind of command to run on the host. And because we have the camp system admin permissions, remember this is not possible if we don't have them, we can actually override the location of that binary with a command on our own container, and then the host will run it. So that's a way to get RC on the host. And this is just the command for that. It's just running this. And the important thing is that we have to have the actual absolute path for the host on the container. So it's using something called overlay file system to basically create a Docker container, and we need to find where in the Docker container we're actually stored, which you can use using, I think, this thing. So you can use something like this. Where's host path? Yeah, set and per directory, whatever. You can use this thing and you can get the host path. But there's an issue. C groups 1 is deprecated years ago. So in Kubernetes, the last time this was used on a modern configuration is 2022. So that's about 4 years ago. So really the chance of you finding this again is very slim nowadays. In Docker, this was deprecated in 2020, so 6 years ago. And basically all Linux distributions run with C groups 2 by default now. And for good reason. They're a lot safer. They make more sense, really. They're also better to manage. So C groups 2 really dominates now, and these vulnerabilities, a lot of these, are basically dead nowadays. And in this case, the server was obviously using C groups 1, So this way of escaping has unfortunately been patched. But there is a third way of attacking. And that third way is using this thing called hot plug. Now, what is hot plug? Well, you have a computer, right? You have your Ubuntu computer running right now, and you have a little USB stick. I don't have one next to me, but imagine I have a USB stick, right? And I just put it into the computer. You'll see a little notification box come up. Maybe something like USB, the name of the USB stick was plugged in or something like that. Well, how does that work? How does the command run to show that little pop-up box when I actually plug it in? Well, it uses something called hot plug. And what this does is basically, whenever a new network device is added, in this case the USB stick counts like a network device, whenever that happens, then this will trigger whatever command we want it to. It will trigger the command that it's currently pointing to. And the important thing is that we can overwrite this ourselves. So this is just a file somewhere, and it's pointing to, I think this might actually be one of those symlinks, where it's pointing to another command. And because we have cap system admin permissions, and we also have cap system net permissions, which basically means that we can actually add both network devices and modify this hot plug. We can use this gadget on the host to create a new network device, change the hot plug to a command that we have on our own container, and then remove the device, which is going to trigger this thing. So basically what the hacker did here is they set a netcat listener on the thing. So they were just trying to get a reverse shell. They created a payload for a reverse shell, and then basically using the same technique to get the absolute path for the container, they found it here and then simply modified the hot plug to call their own binary that they had on the host, which in this case was the reverse shell. And when they added the network device, you can see that it triggered the reverse shell on the host. And I'm sure there are many more gadgets like this than just these. I'm sure there's more ways to escape containers. And really, when you create a privileged container, you have to, be sure that it's running in an environment that's actually, the container is going to be able to escape, because you can literally just mount the whole file system, I'm pretty sure, if you want to as well. So just loads of ways to escape these containers. But it's also pretty cool though, showing a little bit of way here. So checking the privileges, how to do that, and then how to actually build a payload. So I think this report is really good for just looking at how to actually practically exploit inside of a Docker container. And the rest of this was him just trying to privilege escalate from there. So we got root access on the host, and he was then trying to break out of the Kubernetes container using API keys and stuff, but he wasn't really successful. And I'm pretty sure if you want, you can actually try this out yourself. So if you go on Google Cloud Shell, you can do all of these exploits yourself. So maybe if you find a vulnerability, you can report it to Google Cloud VDP. That would be a nice bounty if you found it. Because I actually checked, and the cap, where was it? The cap effect was still set to privileged. So I'm pretty sure you can still escape if you wanted to. So yeah, you can go try that out yourself. But I actually also recommend just reading this report, because it was very nice, and he talks about some very cool ways to escalate inside of Kubernetes afterwards, which is going to be the topic of a video I'm going to make soon. And yeah, I hope you enjoyed this video on some vulnerabilities that happened inside containerized environments. I think it's a super good way of generating high impact vulnerabilities in a location that not a lot of people actually look at. A vulnerability in one of these containers can easily be scaled to high or critical, because a lot of the times it's going to be things like server-side request forgery, local file read, or obviously RC is the big one. So these are very high impact vulnerabilities, and they're very demonstratable impacts. There's no issue getting that high or critical bounty for them, and I think a lot of people do kind of sleep on them as well. If you did enjoy the video, then be sure to leave a like and subscribe to the channel for more bug bounty content to be recommended to your algorithm, so you can grow and get that edge over the competition. Anyways, that's it for me. Thanks for watching, and happy hunting.